Let's start off where we ended with diatomic oxygen. Got the Lewis structure on the left, double bond between the oxygens, and then two lone pair on each of them. Well, on the right, I have the valence orbital diagram for each oxygen. If you recall from a previous section, oxygen has a 2s2, 2p4 valence electron configuration. And this is how you could write the valence orbital diagram. So you can look at this and see, okay, each oxygen has two unpaired 2p electrons. So you go from singly filled orbitals to doubly filled orbitals. But then that would imply that both the single bond and the double bond are equivalent. Because, if you're sharing electrons from the same atomic orbitals, well, that's the problem. You can't think of these as atomic orbitals anymore because this isn't an atom. A molecule is not simply a sum of the parts of the atom. It's something new. So imagine a Cartesian coordinate system. Got your x, y, z system. And typically in chemistry, the z-axis is considered to be the bonding axis. So if you're going to put two atoms together to make a bond, you put them on the z-axis. Why? Why not? So the valence shell for oxygen is 2s and 2p. So we can think of a new orbital in this thing as a combination of the s atomic orbitals. So you take these wave functions, combine them, and you come up with a new wave function. And we're going to call this a sigma bond. S for atomic orbitals, and then sigma, S sigma, go to Greek for the new orbital. This borrows from more advanced bonding theories, valence bond theory, molecular orbital theory. And the sigma bond is a bond in which the shared electrons lie along the bonding axis, along that z-axis. If you look at the one on the right, think of it as a hot dog. So the hot dog is where you expect to find the electron density for the bond that's shared between the two oxygens. Well, we have s orbitals and we have p orbitals. So we have one s orbital from each that combines to make this sigma bond. What about the three p orbitals from each one? You can think of the p orbitals as lying along the x, the y, and the z axes. Not quite, but that's the way we'll think about it. So if you have two atoms coming together, you could have one set of orbitals along the z-axis in each case that overlap each other. So it's like those are the two atomic p orbitals. And then when they overlap, you think of the teal areas as overlapping. I'm using red and teal. That's for phase colors. And then on the right-hand side, you get a sigma bond. All right, it doesn't look the same as the other one. That's because this one's being made from p orbitals instead of s orbitals. You still see the teal area. That's the bonding axis in between there. But that's only one set of orbitals from each. We still have two more p orbitals from each. So we still go back to the Cartesian coordinate system, but now instead of the z-axis, we look at the x and the y-axes. So you think of those as those wave functions, conceptually, being parallel to each other. So when the x's come close, you get the red areas and the blue areas overlapping, and you make a pi bond. So p for atomic orbitals, p turns into pi for these new orbitals, for the molecule. And a way I read some time ago that helps me remember what's what. The sigma bond's a hot dog, I mentioned earlier, and a pi bond is like a hot dog bun that surrounds the hot dog. So a pi bond is one where you have the shared electrons lying on either side of the bonding axis. So you can get a pi bond from the px's overlapping, and you get another pi bond from the py's overlapping. So how do we describe the bonding in ozone? Well, for any molecule, we're going to consider the first pair of electrons that are shared to be sigma bonds. So every single bond is a sigma bond. And every double bond is a sigma bond plus. Plus what? Well, if it's two or more shared pair of electrons, then the second and up, those are the pi bonds. So to sum up what we have, if we have a single bond, we're going to consider that to be a sigma and no pi bonds. If it's a double bond, it'll still be a sigma and one pi bond. And then a triple bond is going to be a sigma plus two pi bonds, for a total of 3. So we're going to consider the bonding to be, at the very least, a sigma bond. And then if it's multiple bonds, you'll have one or more pi bonds.